should have an email curfew.
Yeah. Well, I was up at like 1:30, you know, like figuring out what I was going to say, and it's like, wow, these emails are really still coming in.
Nothing of value is produced after 10 p.m. anyway.
I don't know, we've got the new cover for the book. Okay. All right, so today I'm going to talk about Eilenberg-MacLane spaces, which are traditionally written K of Gn in homotopy type theory. And so like the basic thing that we've constructed, so is Eric here? Yeah, I was talking to Eric Finster a little bit about this, and I'd like to thank him for motivating me to do this because he was talking about how we can do homology or cohomology with it. So that's kind of how we got started on doing this one. But the main thing that we've done, so theorem 1, for any group G, and by a group I mean an explicitly presented group with an H set of elements. For any group G, there is a type KG1 such that pi1 of KG1 is G. And in fact, then the only other thing we need to say about KG1 is that KG1 is a 1 type. Okay? So if you give me any group G, I can make a type whose pi1 is G. Yeah.
And it's a pointed one.
Yeah. Yeah. So it has other properties. Okay. So like I'll uncover some other stuff about it. It's pointed. It's zero connected. And I'll need one more thing about it by the end of the day. Okay. So like it.
Pointed in the formulation because pi1 is something.
Yeah.
Pointed.
Right. That's true. Yeah. Exactly. Yeah. Okay. So what is this saying? This is saying if you give me a group G, I can stick it in pi1 of a type. Okay. And let's see. Just in case the notation's a little unfamiliar to anyone, I put a little background on the board. So I'm going to write, like in the book, I'm going to use the double bar notation for truncation. So double bars A sub n is the n truncation of A, which means that double bar n truncation of A is a type. When A is a type, there's a constructor single bars absolute value of x, which says that x is in the n truncation of A, and then the maps from the n truncation of A into C are the same as the maps from A into C as long as C is an n type. Okay? So that's just n truncation. And the reason I need n truncation is to say that the definition of pi k of a pointed type xx naught is the zero truncation, that is the set of connected components of the kth loop space of xx naught. And what is the kth loop space? Well, the first loop space is the path space from path xx naught. That is like this is the Martin-Luff identity type, id x. And then if I iterate that, then the n+1 loop space is the n loop space in the path type with base point id. Okay? So any questions about like the basic boot up there that we need to state that theorem? Okay. Connected. Have people seen this before? We've been using it a bunch in like the homotopy stuff, but yeah. Okay. So I'm just going to define a type A is n connected if and only if the n truncation of A is contractible. And there are lots of equivalent ways to define connectedness, but that's the one that I'm going to use. So that's saying that if you cut off everything above level n, then it looks like a point. So like any interesting stuff in A is happening at a level above n. So like, for example, the circle is 0 connected, the n sphere is n-1 connected, etc. Okay, good? Okay, and then the interesting part about KGN is number 2 here, which is for any abelian group G, there is a pointed type KGN for any positive n, or for n greater than or equal to 2. There's a pointed type KGN such that pi n of KGN equals G, and pi k of KGN equals 1 otherwise. Okay? So I can make a type that has G in its pi n and is trivial otherwise. Okay? And these are what are called Eilenberg-MacLane spaces, or KGNs. And the KGNs are useful because they're kind of basic building blocks that you can use to put together spaces up to homotopy. So any, I think someone told me this yesterday, Carla told me this yesterday, any strict infinity groupoid can be constructed by just producting together KGNs, because you can just kind of like smush them together. And then if you want more interesting things, you have to look at the Poznikov towers and get the interactions between the various homotopy groups, et cetera. But they're kind of a basic building block that's good to start with. So for a while, we wanted to know, how do we construct these things? How do we make KGNs? And today I'll tell you that.
Are they unique in some sort?
Are they unique? Yes, because we have Whitehead's theorem for n-truncated types. And KGNs are, in fact, n-truncated, which means that up to homotopy, any other type that has this same characterization of the pi n's will be equal to KGN. Okay? Okay. So the rest of the talk is, how do we make these things? And I guess like the main points here that I want to, like, why is this a fun proof to do? Well, we're starting to have some useful lemmas. For example, I'll use Peter Lumstein's proof of the Freudenthal suspension theorem that we formalized in AGDA in the construction of KGNs. And the other interesting thing to me is that this this construction is kind of entirely type theoretic, or I don't know, like it's in the, uses like the encode decode style proofs, or whatever you want to call that. And this is kind of by definition, because like, there's not a precise line between like the homotopy theoretic proofs and the type theoretic proofs, but some of them feel more calculational, and those are the ones that I'm able to like understand and do. And since I did this, this is one of them, kind of by definition. But like, it's kind of cool to see calculations with the type theoretic structure coming out here. And then the other thing is that this is all formalized in AGDA. Okay, so let's make some KGNs. Let's do one first, though I don't want to get too bogged down in one, because it's kind of a construction that other people have done in various guises. So it's like kind of the easy part. So I'll suggest that. So this is an attempt to informalize this proof, and we'll see how that goes. Right? So like, I've got a lump of AGDA code, and I'm trying to figure out how to explain it to a person. So work with me if things aren't clear. Okay. So we're going to define KG1, given a group G, as a higher inductive type. In particular, it's going to have the following constructors. It's going to have a base point, which will have type KG1. Okay, and like really, it's like K1 of G, but I'm going to continue to write KG1 since I'm doing informal stuff. In AGDA, I can use mix-fix operators if I want to do that anyways. Okay, I'm going to have a constructor base, which is a point. So now we've satisfied the requirement that it be a pointed type. I'm going to have a constructor level that says that KG1, K of G1 is a one type. So I'm using Guillaume's kind of definition where we just put in the fact, we use like a higher inductive definition where we directly specify that something is of a certain level, which you can unwind into other constructors if you want, or you could separately define an inside thing and then truncate it after the fact if you want. But no? Okay. Okay. So like last semester, Guillaume proposed a notation like data kg1 colon type sub 1. Okay. Which means that I'm simultaneously defining this type and truncating it. Okay. And if you want, you can implement this kind of notation by saying, first I'm going to define something like that. Let's call it k prime g1. And then define kg1 to be k prime of g1, and then 1 truncate it. Okay. But like it's, yeah.
It doesn't work. You cannot first define the type and then truncate. You need to truncate at the same time.
Okay.
To define the type.
Okay.
Recursive arguments in the type.
Okay, so you can't do that. What you can do, fine. The other thing you can do is you could just spell out, so basically like, yeah, okay. What you can do is, if you want, you could just include a constructor. So like we know how to put in constructors that add the appropriate path. So if this were any n, any fixed n, we could put in the appropriate constructors that truncate the type as you're constructing it. Okay? I think a better notation than that is to just put in a constructor that says that it's a one type. Mike and Peter and I have talked about how to make sense of this. So like basically, in all circumstances, the notion of being an n-type turns out to be the kind of thing that you can put in constructors for. So like when it's contractible, you're putting in a point constructor and a path constructor, and otherwise you're putting in a path constructor. So you might as well just put in the fact that it's a one-type directly and not worry too much about implementing that with other higher inductive constructors. But this can be reduced. Guillaume showed how to reduce this to the usual schema for higher inductives if you're worried about it.
So when you expand it, it's actually because.
Yeah, right. So like if we expand it in this case, yeah. So let's see. If we're going to say that it's a one type, then what do we need to say? That every x, y, colon, kg1. So let's see. How high do we need to crawl up here? pq colon path x, y, rs colon path pq, p equals q. Is that right? R equals s, sorry. Yeah, duh. Yeah. So in this case, saying it's a one type is saying that it satisfies that uniqueness of identity proofs, right? Okay, so we could just put that in. The way I phrase it is just, hey, it's a one type. Okay. Okay.
Level is a residue from H levels.
Yeah, or type level, right? Like, yeah. I use the word level for being of level n. Yeah. Okay. My indexing here is starting at -2. I guess people figured that out. Yeah. Okay. So we have that. And then the next thing we need to say is that loop on the unit element of the group G equals the identity on the base, and loop on, oh, man, got tripped up. Okay, duh. Okay, good point. Loop, the main point, says that every element of the group G produces a path from the base point to the base point. Okay, because remember, I'm trying to put G into pi1 of this type. Okay, so obviously I need that every element of G determines a path from base to base. And then I need functoriality of that. So loop of 1G equals id, and loop composition says that loop of, I'm going to write it as composition in G of x, y equals loop of x, or actually it flips around here, loop of y compose loop of x. And that's just because my path composition is in the like function composition kind of order, but my group composition is in the like transitivity kind of order. Okay? Okay, so stare at that for a second. Yeah.
Staring at it. It's nice to have an explicit presentation as a higher inductive type.
Yeah.
But there are also constructions of this thing that we know from other things like this RESC completion construction.
Yeah.
Or you could do it as a groupoid quotient.
Yeah, exactly.
That would give the same
Yeah.
result, right?
Yeah. So I think this is basically, I started to write up the groupoid quotient and then like didn't want to deal with like the actual indexing being unit, so I just kind of specialized it. But I think this is exactly the specialization of the groupoid quotient to groupoids that happen to be groups, right? Yeah.
Does the definition of pi 1 turn the order around again so that we get it right?
Yeah. Yeah. I mean, the definition of, I mean, group composition is just like, read it as like x semicolon y there, right?
I mean, you're reversing the order of x and y.
Not really, because my composition is backwards. Like the way you're thinking about the composition is backwards in the two, right? So like my,
No. I mean, eventually you're going to take the composition and make pi 1 and make
Yeah.
a group, and it's going to be improved. And I'm just worried about
Yeah.
whether that group is going to be G or it's group with the opposite multiplication.
I think it's going to be G, because the composition for path, when I make the path group, the composition is going to be in this order, right? It, yeah.
In a way, a group is isomorphic to its opposite.
Sure. Yeah.
Is this supposed to be some sort of generalization of the Cayley representation of the group?
I don't know.
No.
I don't think so.
Can you explain what Steve was mentioning as the connection with the REST completion?
No. Maybe Steve can.
Okay, so
Yeah.
if you wrote that comp
Yeah.
the way mathematicians do, you would write x, y.
Yeah.
Or y, x. Which one would you write?
I don't know. How do mathematicians write it? Like in a group, so like if I think of like x times y, is it like in function composition order or
No,
like?
it's the given operation, and you're not just accidentally turning things around. It's the group comp.
Yeah, it's the group composition.
Okay.
Yeah, right. So like I would think of it as like function composition is backwards from everything else in the world, right?
Yeah.
My path composition in my library, and I didn't want to flip things around because I would get confused, is in function composition order, because I think of the paths as like equivalences in univalence, et cetera, like function composition. So all of my paths are in function composition order as opposed to in diagrammatic order, right? So like if we wanted in like the Coq library would write loop x at loop y and no one would have to complain. And I can maybe try to do that, but like, yeah, okay. Yeah, that's it. Okay, so then you get an elimination rule. Everybody can like derive the elimination rule for this higher inductive. Let's see, I can do the simply typed version. If you read off what you would get if you just like kind of take those constructors and compact the definition a little bit, then what you get for the simply typed version is that if you want to define a map from KG1 into C, where, so I'm going to write it in the like maps from KG1 into C are the same as proofs that C is a one type. Yeah, so maps from KG1 into any C, where C is a one type, are the same as finding a base point in C and then giving a group homomorphism between G and what I'll call the, I don't know what to call this guy, the group of loops in C with base point base prime. So given any one type C, we can make a group here whose elements are the paths from, so given any pointed one type, so the point is base prime here, we can make a group whose elements are paths from base prime to base prime, whose multiplication is composition, dot, 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 et cetera. Okay? pi1. Yes.
It's not,
No, it's
pi1
not.
because it's
No.
one type.
Yeah, it's, yeah.
It happens to be pi1 because it's a one type.
Right. Yeah, so I'm not truncating here, right? I'm like insisting that it already is a one type and then taking the group of loops. Yeah, so it's just like, it's equivalent to pi1, but yeah. Okay, but I mean, this is what you expect for like the groupoid quotient kind of thing too, because when you do the groupoid quotient, you say that a map from the groupoid quotient into some other type is a functor, right? And I'm just spelling out, yeah. Okay, so like that's how we make maps out of KG1. And then there's of course a dependent lim, blah, 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 but I don't think we really need to get into that. Okay, so like to make KG1, we just make it as a higher inductive like that. And then what we can prove, theorem, is that omega of KG1 equals G. Okay? So this is just like proving that the loop space of the circle is Z, except we're going to do it. So like KG1 really, if you haven't noticed this already, is very analogous to the circle, where I have Z in its pi1, right? So K Z1 is the circle, right? And I'm doing the same thing, and this is really a lot like the proof that the fundamental group of the circle is the integers, except I'm doing it for an arbitrary group. Yeah?
Does it define a circle through a generator of Z as
Yeah.
opposed to all the elements?
Yeah, exactly. So it's a different presentation, right? So
This is not entirely true.
this is true if I mean homotopic to, I mean homotopic equivalent to. Yeah. Theorem. Right? And in fact, like by Whitehead's principle, that's just going to follow from what I'm going to do today, because I've calculated that they have the same homotopy groups and they're both one types. Yeah. Okay. But so like we need to do this proof, and I'll basically just set it up for you, and then the rest is kind of a calculation. So if we want to prove that the loop space of KG1 is G, then what we really mean by that is that the paths in KG1 from the base point to the base point, regarded as a group, but let me just do the like bijection on the underlying sets part of it, is G, right? So as types, I want to show that these two types are equal. Okay. How do I do that? Well, whenever I go to show that the paths, the loops in something are equal to something, I need to generalize. Okay. So I'm going to say that for all x in KG1, the paths in KG1 from base to x equals what I call the codes fibration for x. Okay. And the idea with the codes is that this is another fibration also over KG1 that provides a more explicit description of what the paths are. Okay? So that's kind of like, for the circle, that's the universal cover of the circle, and that tells you sort of, as data, what these paths turn out to be. Okay?
Universal quantifier is not so good. Can you just write the words?
Pi.
Or pi, okay.
Yeah. Okay. Read for all is pi if you ever see it today.
Does this code X correspond to something standard in classical homotopy theory?
I don't know. For pi1 of S1, it corresponds to the universal cover. Maybe when I define it in a second, somebody can tell me.
It's called EG1.
Okay. It corresponds to EG1. Yeah. Okay. All right. So how do we define codes, or EG1? Well, the point is that codes is a fibration over KG1, right? So it's a map from KG1 into the universe. So of course it's going to be defined by KG1 recursion, right? We use that universal property that's up on the board up there, taking the result type to be type, and then filling in the premises, okay? So the first thing we need is a point of the universe, okay? And so we need a type. And so what we're going to do is we're going to send the base point to, so now we need a type, and let me just be a little bit more precise here and write L of G for the elements of G, just because that's how it is in my notes.
Assuming G is presented, you've already used that before. You didn't show us what G is.
Okay, so G by G I just mean,
G consists of LG and
yeah, exactly. Yeah. So group is a record with elements, which is a type, and then I think I called it like elements level, which says that elements is a 1 type, is a 0 type. And then there's an operation comp, which is L, arrow, L, etc. Okay? Yeah, so it's just an explicit presentation. Okay? Okay. So if I'm precise about it, I should really write elements of G rather than relying on an implicit coercion there. Okay? But all right, so like what I need is a fibration over KG1. And if I'm going to get this as a corollary of this, then it had better be the case that codes of base equals elements of G, right? So that one is determined. Okay. And then what we need is a group homomorphism from G. So we need a map of groups. So a map, let me write it like, so we're going to send, well, okay, so we need a group homomorphism from G into the loops in type with base point KG1. Sorry, no, with base point elements of G. Okay? So I need a group homomorphism from G into the group of loops in the universe with base point G. And the way that I make that, so if you unwind what that is, then the key thing is that for all G, which are elements of G, I'm going to need a path in type from elements of G to elements of G. Okay. And then I'm going to need to show that this assignment of paths is functorial, so that the identity element of G gets sent to the identity equivalents, and so that the compositions get sent to the compositions, et cetera. Okay? Good?
By the way,
Yeah.
somewhere in the background, you're going to make sure that you're really not using all of type. You're using something like type 1.
Yeah. Well, maybe, since like in Agda I'm still using type colon type, but yeah. Like, I think this all works with universe levels. But yeah. Yeah. Okay. Right. Okay, so how do we do that? So like, given an element of G, we want to determine an isomorphism between elements of G and elements of G. And of course, what we do here is we send G to composition with G. Okay. So for any group element, composition with that element is an equivalence on the group, on the underlying set of the group, right? Okay, what's the inverse? Well, if I send G to composition with G, then the inverse equivalence would, of course, be composition with G inverse.
G is a group element. It's really multiplication by G.
Yeah, comp is my notation for.
I'm just wondering why it's called composition.
Okay, fine. Because it started off as a record for groupoids, and then I got sick of all the like implicit arguments and decided to just do the special case of groups. Yeah. Okay? Okay, yeah. So I'm sending G to, let me just write it as like G times blank. Okay? Good?
And
Okay.
it's the Cayley representation. No,
No,
way.
No, you were right. Okay. Okay. And so like multiplication by G is an equivalence because the inverse map is multiplication by G inverse. And right, when I compose those, then I just collapse the inverses and I get back where I started. It sends the identity to multiplication by the identity element, which is the identity function. It sends the composition to multiplication by composition, which by associativity is the same as composition by one and then composition by the other, so we get a group homomorphism. Okay? Okay, so that's my code's fibration. And I guess it's the Cayley representation. Good.
What's that other argument there?
So like where this says that multiplication by G is an equivalence. Right. Yeah.
So the top four in your first premise was C is a one type,
Yeah.
but you don't seem to have that satisfied.
I do. Why do I do? Let's see. Where? Oh, yes. So codes goes into 0 type. Yeah. Right. So let's see. Yeah. Okay. So right, because I was doing this off my notes. Yeah. Codes in fact goes into 0 type, and then you can observe that elements of G is in fact a set, right? We stipulated that when we defined what a group was. And then like there's a little bit of nonsense that I'm leaving out here because really what I need is a path in 0 types between those things regarded as 0 types. But a path in 0 type is the same as a path in type because the fact that the rest of it is being a 0 type, which is an H prop, so it's irrelevant. Okay, so like in the code there is this stuff, and like, but like basically don't worry about it. Okay? Okay. Good? And then basically now, given that I've told you what the code's fibration is, this thing is what I would call a routine calculation. Like you can define maps back and forth and then check that they're the identity. One of the maps is transporting along the codes. The other is just the loop constructor. And then like you calculate and check that they're identity. Okay. So I'll maybe do one of these kinds of proofs later, but I wanted to do a more interesting one if I do one of them at all. So you can either do this yourself or read the AGDA code if you want to see how you calculate this out. But by the time you've got the fibration, basically you just like calculate and then you're done with the proof. Okay? Okay. So that's KG1, right? So what we've shown so far is that the loop space of KG1 is G. Okay? We already stipulated that it was a 1 type, so now that we know that it's a 1 type and it's got the right pi1, it's also really easy to check that KG1 is connected, by which I mean 0 connected. Okay? And the reason is, well, it's got a point, that's the base point, and then we want to show that in the truncation, every other point is equal to that point. And that's easy because the truncation kills anything hard that you'd have to do. You just do a KG1 induction, and for the point for base, it's trivial, and then for all the other stuff is just trivial by h-level reasons. Okay? So it's easy to show that KG1 is connected. So what we've got now is that KG1 is a pointed, 0 connected 1 type with the right group in its pi1. Okay? So that's a pretty good characterization of pi1, or sorry, of KG1, right? That's the properties we would expect for KG1. I'm going to need one more fact about KG1 before the end of the day, which is that and this is very much inspired by Guillaume's proof for pi2 of S2, though it's a little bit different. So what I'm going to need is that definition, a coherent H structure on a type A, pointed type A, so let me grab an A naught in A, is, okay, 1, a multiplication operation, A, arrow, A, arrow, A. 2, I want this to be unital in the sense that for all x, multiplication by, or actually I'm going to need a name for this. Unit L says that for all x, multiplication by a naught x equals x. Similarly, on the right, x times a naught equals x. Okay, so bear with me. I'm just like making an auxiliary definition here. It's one that's come up kind of before. Okay, but you'll see why I need it in a second. So it's a multiplication operation. It's units on both sides. Okay, it's got to be coherent in the sense that with this data, there are now two ways to prove that a naught times a naught is a naught. I can apply the left unit or the right unit, and I want to say that those two agree. Unit L of a naught equals unit R of a naught. Okay, and then I want that for all a, multiplication by a is an equivalence. Okay? So this is pretty close to a definition that Guillaume was using in his proof of pi2 of S2, though I don't think the coherence requirement came up for him. Did it?
No, but maybe I did it anyway. I didn't
Yeah.
formalize the proof, so
Okay.
maybe I used it.
Yeah. Okay. And so what I'm going to need before the end of the day, I don't know. I can just tell you what I needed, and I don't know. Okay. I mean, so like it comes up for a. Yeah. Yeah. Right. Yeah. So like, I mean, these are paths, right? So like, I'm not putting any h-level restriction on A. So like, unit L and unit R are a choice of paths, and they can agree or not. Okay. So the one additional fact I need is that if G is abelian, then there is a coherent H structure on KG1. Okay? So what I'm going to do is I'm going to make this multiplication operation on KG1, and then I'm going to use this multiplication operation when I go to prove that pi2 of KG2 is the same as G by way of showing that pi2 of KG2 is the same as KG1. Okay? So this H structure is a technical device that I needed to get that proof to go through. There might be another way to do that proof that would use a different notion. I don't know. It's just something that worked. Okay. And the way that you make the multiplication, right, is that, so what we want to say, let me just show you how you make the multiplication. So if you define so the multiplication wants to be a map from KG1 to KG1 to KG1. Okay. So how do we define a map from KG1 to something? Well, we use KG1 recursion. Okay. So I need to send the base to something, and then I need to send the loop on an element G colon G to some thing that shows that it's compatible with the loop, right? I need to write my functor here. So I'm going to send the base point to the identity function. And then here what I need is essentially a path. Well, for every element G of G, I need a path from lambda xx to lambda xx in KG1 arrow KG1. Okay. But a path from lambda xx to lambda xx in KG1 by function extensionality is, for every x, a path in KG1 from x to x. right? So it suffices to show that. Okay. And how do we do that? Well, we do that by, this is in KG1, so we do it by KG1 elimination. So I need to send the base point to a path from base to base, okay, to something which is a path from base to base. But over here, I got an element of G, and I know that the paths from base to base in KG1 are exactly determined by, well, are not exactly, but are determined by the elements of G. So I send the base point to the loop at G. Okay? And then when I'm doing my KG1 induction, the coherence constraint here is that for any loop G prime, okay, I need to show that this assignment of a path is, respects another loop in KG1. And what that amounts to is showing that there's a path between loop G and loop G in the fibration x dot path xx over loop G prime. Okay? Using the path over a path notation, right? You can unwind it into a transport on either side if you want. But if you unwind what this path over a path means, it means exactly that I need the following square to commute, where the following square has loop G over there, loop G prime over there, or sorry, loop G over there, loop G prime on that side, and loop G prime on that side, okay? Because a path in XX, right, is just like the naturality. This is functorial action of the Hom functor, so it's pre-composition on one side, post-composition on the other, okay? Okay, how do I know that this commutes? Well, I know that loop preserves compositions, right? So this is the same as asking that loop of G compose G prime equals loop of G prime compose G, which is exactly the abelianness that I stated as a requirement of the theorem somewhere that I think I erased. Okay? Yeah. So like theorem, if G is abelian, then there is a coherent H structure on KG1. Okay? And the reason that we would expect to need G to be abelian here is that what I'm going to do then is show that, use this as a lemma to show that, for example, pi 2 of KG2 equals pi 1 of KG1 equals G, okay? But we know that pi 2 of anything is abelian, right? All of the higher loop spaces are abelian. So it better be the case that somewhere I input some abelianness, okay? Because otherwise it'd be showing that this group, which is abelian, is equal to this group, which is not, okay? So you would expect that abelianness would come up somewhere. And for me, the place where it came up was in needing this coherent H structure on KG1 to do the proof here. Okay? So you can think of, basically, I think, I haven't checked this, but by an Eilenberg, what's the name of that thing? Ekman-Hilton, thank you. By an Ekman-Hilton argument, you should be able to show that for any type with a coherent H structure on it, its pi 1 is abelian. Okay? Because you've essentially got the two multiplication operations. Okay? Good. Okay, so summary, KG1 is a zero-connected, pointed, zero-connected one type with pi 1 equal to G and a coherent H structure. Okay? Good? Okay, so that concludes the KG1 part of the talk. How are we doing on time? Good. Okay, so now what I'm going to do is describe how we do KGN. And so now what we need to do, let's say, is like KG2, KG3. And one way to do it is we could try to give a direct higher inductive description of like, well, now I take the same thing. So I have this like technology for doing iterated loop spaces that I used in the first proof of pi n of Sn. And we could try to like directly stick G into pi2 of a space and then pi3 of a space, dot, 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 dot. Okay. And I thought about doing that, but that seemed kind of annoying. And we have a bunch of technology that we've developed now that we can put to use here. So I'm going to give a kind of more abstract definition, which is really kind of exactly what you would expect. Because if you want to do kzn, right, how would you define kzn? Well, you know that that's, if you take the n sphere, then the n sphere is trivial up to level n, and then has z in level n. Okay, so if you wanted to make kzn, you could take the n sphere and then n truncate it. Okay, and the way I'm going to build kgn is by doing exactly the same construction that you do here, except I'm going to replace the circle with kg1. So I've shown you how to make kg1. And what I can do is take kg1 and suspend it n-1 times, and then n truncate it to get kgn. Okay? So I take my type that has g in its pi1. I use the suspension. So remember, suspension is a higher inductive type, I guess sigma, with points north and south, colon. So suspension of A is a type. North and south are suspensions of A. And then there's a constructor meridian that goes from A to paths in the suspension of A from north to south. Okay. The picture is if I have north and south and A sitting in the middle, then for every point x in A, I'm adding in a path from north to south. Okay? Good? Okay. So I can do that, and I can suspend it n-1 times to boost it up to level n. So that's how I get a type with G sitting in its n, and then I truncate to kill everything higher. So the n truncation just kills everything higher than n. This process will produce suspensions, preserve connectedness in a way that I'll talk about that says that everything below n is trivial, and then I'll prove that n is the correct thing. Okay?
So if in fact kg1 were S1,
yeah.
you would be getting the previous thing.
Yeah, exactly. Right. Yeah, because like you can define Sn. I mean, you can define it recursively by n, or you could just say it's the n-1 suspension of the circle. Yeah. Yeah. Right. Because like S2 is the suspension of S1. Right. So that's why you get the -1. Okay. So I think this is a nice way to build KGN that's kind of parallel to the way that we traditionally build the n sphere, and avoids having to like muck around with higher inductives with like things in their nth loop space, even if that is kind of like fun. Okay. Good. So then the theorem is that pi n of kgn equals g, and pi k of kgn equals 1 otherwise. Okay. And how do I want to do this? Whoa. So, for example, why is it true that, so like basically we need to consider 3 cases, which is k is greater than n, k equals n, and k is less than n, because the reason that this theorem holds is kind of for different reasons depending on those 3 cases. Okay. If k is greater than n, then what we're looking at is pi k of, okay, and I'm just going to start writing kn here just because g is fixed everywhere, right? Okay. So pi k of kn, where, let's consider the case where k is greater than n. Pi k of kn equals the 0 truncation of the kth loop space of kn. Okay? Right? So it suffices to show that the kth loop space of kn is equal to a point, right? So we want to show that in this case, you know, to show that this equals 1. It suffices to show that the loop space is equal to 1 because truncations preserve 1. Okay? And the reason that the kth loop space of this is 1 is that by definition, kn is the n truncation of something. Okay? So kn in particular is an n-type. And it's just a general fact that if k is greater than n and A is an n-type, then pi k of A equals 1. And for the rest of today, I'm just going to be totally sloppy about pointedness. If you want to check that all of these things preserve the point, then it's in the code. Okay? Okay. But so basically, when you take an n-type and you look at an iterated loop space that's above level n, then it's obvious that it's 1 because you've killed everything up there, right? So this is just like a simple induction to check that. Okay? So the case for k is greater than n is really easy. Good? So now what we've got is something where above n it's easy, and now we just need to check that these work. Okay? So how do we check that those work? Well, there are many ways we could imagine doing this. In particular, this one follows from a proof of Guillaume's that's in the book. There's lots of routes to that. That's basically the same as Guillaume's proof that pi k of Sn is 1 for k less than n. Okay, but the way that I actually wrote the code was a little bit different because when I was doing this, we'd just proved a theorem, and I wanted to derive some corollaries from that theorem because it was kind of fun. So the way I'm going to do this, and we'd need the theorem to do the diagonal anyways, so it's not really that much different. But the theorem in question is something called the Freudenthal suspension theorem. And after Guillaume and I gave a proof of pi n of Sn, Peter Lumsdaine looked at that proof and was like, oh, we can do Freudenthal. Okay? And then Peter and I formalized it, and so we have a proof of the Freudenthal suspension theorem. Peter talked about it at Andre's symposium on Monday, or Monday, whatever number of weeks ago. Okay. Okay. But the basic point with the Freudenthal suspension theorem is that the corollary that I'll need, and I can go from the thing we actually proved to this if I have time, but let me just say this for now, is that the corollary that I'll need is that if k is less than n, or k equals n, and both of those are greater than 1, okay? So under certain conditions on k and n, what we get is that pi k of kn equals pi k plus 1 of k n plus 1. Okay? So from Freudenthal, I can prove this, show you how we got from our proof of Freudenthal to this if I have time. But the main thing that we get from Freudenthal is stability of the homotopy groups of Kn in a certain range. And this is exactly the same range in which the homotopy groups of the spheres are stable, because Freudenthal works by connectedness of the thing you're talking about, and the thing we're talking about is the same connectedness as the circle. Okay? So if you're used to this chart of homotopy groups of spheres, then this should be familiar. But the basic idea is that if we write out like pi 1, pi 2, pi 3, pi 4 on that axis, and k1, k2, k3, k4 on that axis, then what Freudenthal tells you is that certain diagonals are the same. So in a certain range, you know that the diagonals are consistent. And in fact, because we're doing KGNs and not spheres, I've already killed, let's see, like all of, where's the diagonal? There's the diagonal. So like all of this stuff, right, we know is trivial already, because that was the k is greater than n case. Okay? So if I didn't screw that up, we've already killed that stuff. And so what we need to show is that this diagonal, did I get that right? Is G. Okay. And this diagonal and this diagonal and this diagonal is 1. Okay? So like if you visualize it that way, Freudenthal is going to tell you certain stability questions. So like, let me not mention Freudenthal for a second. The problem is to show that these diagonals are consistent, right? Because if we do that, then we get that pi n of kn is G and pi k less than n is 1 otherwise. Okay? Freudenthal tells you that starting here, these are consistent. So for example, it tells you that pi 2 of k2 equals pi 3 of k3 equals pi 4 of k4, dot, dot, dot. Okay?
Consistent, you mean all the same?
All the same, yeah. Yeah. Right? Stable. Yeah. Okay? So it tells you that like these are all the same. And it'll tell you that, for example, pi 1 of k2 equals pi 2 of k3, dot, 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 dot. Okay? So it tells you that the diagonals are all the same. So if I want to finish my proof, it suffices to consider the first point in each of the diagonals, because I need to bootstrap myself by making this link here and identifying a 1 there and a 1 there, dot, dot, dot. Okay? And then as a corollary of Freudenthal, I'll get that I get the result I want. Okay? So it's kind of a fun application of Freudenthal. In this, there's kind of a proof that pi n of Sn that kind of falls out rather naturally, right? Where k is the circle. Okay, and so that's what we need to do. And so what I did was to show Bye, eraser. Okay, so what I did was to show A, that k, for k less than n, pi 1 of k n plus 1 equals 1. Okay, so that's this pi. Okay, what I did was to show that, yes. So that, sorry, that's starting off all the k less than n diagonals, right? So like, therefore, pi k of kn equals 1 for k less than 1 by that chart. Okay, right? And good. Okay. Then show B to show, so now to show that pi n of kn equals G, it suffices to show that pi 2 of k2 equals pi 1 of k1, because we already showed that pi 1 of k1 was G. Okay? And then C, so like if, to finish the proof, that like, you know, that corollary of Freud, I need to prove that corollary of Freudenthal. Okay? So to complete the characterization of kgn, we need to show A, B, and C, where C is the fact that that, in fact, that like stability characterization follows from Freudenthal. B is the fact that pi 2 equals pi 1, and A is the fact that this is trivial. Okay? Okay, so this one is really easy, and I'm not going to do this one because Guillaume's done it, etc. Okay? All right, for those two, let's see. Which do you want to see? B? Okay. B. I was hoping you'd say that. Okay.
Now I got that beer.
What?
Now I got that beer.
Now you got what?
The one we agreed on.
Oh.
Okay, later.
Yeah. I'm just feigning ignorance. Okay, B. All right, so what we want to show is that pi 2 of k2 equals pi 1 of k1. So this is basically, if you want to think of it, another proof that pi 2 of s2 equals z. In the specific case where k whatever is whatever. Okay. So really, let's do the calculation. What we show is that pi 2 this one? Yeah. Okay. Which one? Sorry.
You already raised it.
Okay, sorry. Yeah. I've got the notes here if you want to. Yeah. Okay. Sorry for the bad board management. Okay. And so let's see. Where are we going to start? Proposition. If A is, let me do the calculation outside in, and then I'll get to that. Okay. We want to show that pi 2 of k2 equals pi 1 of k1, right? We know that by definition, pi 2 of k2 equals the zero truncation of the double loop space of, sorry. Yeah, no, that was right. Zero truncation, double loop space of k2, right? But we define k2 to be something. In particular, we define it to be the two truncation of the sigma 2 minus 1.
That's really not board management. Write the thing and then write another line, okay?
Okay.
Thanks.
K2. Good?
And then now write.
Definition. Yeah. Equals double loop space of the two truncation of the suspension of 2 minus 1 of k1. Right? That was just the definition of k2 is the 2 minus 1, that is the suspension of k1. Right? Good? Okay. And we want to show that that equals well, what we'll in fact be able to show is that we want to show that that equals, at the bottom, pi 1 of k1. Okay, but what is pi 1 of k1? It's the zero truncation of the loop space of k1. Okay, and then what do? We okay, so I think the first thing we want to do is to rotate the truncations, right? So there's this general fact that truncations and loop spaces swap around, changing the indexing a little bit. So let me just move over here. Okay, so suffices to show that the double loop space of the suspension of k1, 2 truncated, 0 truncated, like there's some cleanup that's going to happen, so if that looks a little bit unwieldy, that's okay, is the 0 truncation of the loop space of k1, okay, like that. And now we can commute the truncations and say that, pull out one truncation, and say that this is the loop space of the one truncation of the loop space of the two truncation, man, this is heavy, sorry, k1, blah. Okay, good. And that's just swapping around this first loop space and the outer 0 truncation. Good? Okay? Okay.
These laws for commuting
Yeah.
truncation with the loop space are something that was done
Yeah.
a couple of months ago.
Yeah.
And it should be stated as a kind of extra lemma. But
Sure. Yeah.
We,
I mean, it's like,
we've all gotten used to seeing you do that.
yeah. Okay. Right.
Maybe you can just write down on the side what the lemma is.
Lemma the K truncation of, in this case, I just need the loop space of A, equals the loop space of the K plus 1 truncation of A. Okay? Good? Okay. And now I'm a little bit off script, so I'm trying to recover here. Good. Okay. So it's going to suffice to show, okay, so therefore, it suffices to show that this bit, let's see. Yeah, so I want to rotate, yeah, so like, I want to rotate here. I'm doing this a little bit differently than I had prepared, so just bear with me for a second, and then I'll be back on script. I can rotate here and do that, okay? So I rotate there and do that. So it suffices to show that this bit equals this bit because there's an omega outside of each of them, right? But what I know is that the one truncation of K1, well, K1 is a one type, so the one truncation of K1 is just K1, okay? And so it's going to suffice to show that the loop space of the two truncation of K1, one truncated, equals the K1. Okay? Good? That's just this bit equals this bit. Sorry, this bit equals this bit. Right? Okay. And like, we're going to get down to the interesting bit in a second now. I just need to kill that truncation. And the reason is that yeah, I should have just done this the way that I had it. The two truncation. So let me write down what it's going to suffice to show, and then I'll try to recreate the reason why it gets there. It suffices to show, at the end of the day, what we're going to end up showing is that the whole loop space of the suspension of K1 is equal to K1, okay? Which is almost what I have on the board up there, except I've got some truncations that are going to turn out not to matter, okay? And the reason is that if I show this, oh, okay, so that's like pi, yeah, okay. So like basically taking a truncation, if you're looking at a pi that's less than the level where you're truncating, then taking the truncation doesn't hurt you, okay? So if I can show this, then I can insert those truncations, right? So this top bit is the same as, well, right, like, yeah.
But I think this is false, right? Because if K1 is KZ1, which is S1.
Yeah, sorry, I lost a truncation. Sorry. I still want the one truncation there. Yeah. Yeah. Yeah, that's better.
Just rotate the innermost two truncations.
Yeah. Yeah, that's one way to prove it. Yeah.
Then it
Yeah.
becomes one. And you
Yeah.
have one truncation twice.
Yes, good. Yeah, that's one way to prove it. The other way to think of it is just that, like, that's a, let's see, that's like kind of like a pi or something like that. And basically, yeah, like, okay, done. Okay. Okay, thanks. Yeah.
Let me observe that this equality
Yeah.
would make sense for G non-abelian. I mean,
Would,
and then it would be false.
yes. Yeah.
In other words,
Yeah.
this is not trivial because you need to
Right.
use the abelianness.
I do. Yeah. So in fact, like, I kind of went off script here, but what I was trying to get to proving as a lemma was that if A is this stuff, not this stuff, but if A is a pointed zero-connected one type with a coherent H structure, okay? So if A is a pointed zero-connected one type with an H structure, coherent H structure, then the one truncation of the loop space of the suspension of A equals A. Okay? And the H structure that I'm assuming here is exactly what's giving you the commutativity that you need for the theorem to be true. Yeah. So the H structure, remember, the reason I brought it up before was I was going to say it's how we bridge pi 2 of k2 and pi 1 of k1. Okay? And this is exactly the spot where it comes up. And I got a little screwed up there because I was doing this calculation in the notes in generality, but hadn't introduced the generality yet. But basically, the thing is that we can then just replace k1 with A here. Ooh, don't replace it. Okay. I can just, suffices to show this. This is the same formula for general A. Yeah, yeah. Okay? Okay. So now if I have any A like that, I want to prove that fact, and then I'm done. Okay? And the way that I prove that fact is by another one of these encode-decode proofs, because now I'm in the situation that I'm pretty fond of being in, where my task is to characterize the loop space of some type. And we've got a really good technique for doing that that works at least at or below the level of the generators, which is where we are. Okay? So I want to prove that the one truncation of omega of sigma of A, one truncated equals A. Okay. Of course, that's the one truncation of the paths in sigma A from north to north equals A. Okay. Whenever I go to characterize a loop space, I'm screwed, so I generalize and characterize a path space. So for all x in the suspension of A, I'm going to show that the one truncation of the paths in suspension of A from north to x equals some codes of x, where codes is some fibration that I'm going to define over the suspension of A. So codes is going to go from suspension of A into type this time. We won't need to do anything fancy with going into one types. Okay? And the definition of codes is by suspension rect. So I'm going to send north to something, south to something, and the meridian for A colon A to something. Okay? And what do I send them to? Well, I want that codes of north equals, sorry, I'm writing n, not north over there. Codes of north I want to turn out to be A, right? So that choice is fixed. And then I just need to fill in the rest such that the proof goes through. But I can do that. And let's see. For south, we can also send south to A. And then we need to send the meridian, given an element of A, to a path in type from A to A. Okay? A to A. Okay. So I've got an element of A, and I need a path from A to A. Well, I assumed that A had an H structure. One of the points of an H structure is that there's an operation of multiplication that's an equivalence. Okay? So I send this to, I think I wrote it as circle dot, A times blank, which is coming from the H structure on A. Okay? So the reason I brought up the H structure is that it's the thing that lets me construct the code's fibration. Okay? And then, what? Oh, yeah, and univalence, of course. Univalence axiom applied to that function paired with the fact that it's an equivalence that also comes from an H structure. Yeah. Yeah. Okay. So now, what we need to do is calculate that this all works out. And the two facts that I need about this code's fibration in order to do that calculation is that transport at codes with the meridian of A on A prime equals A multiplied by A prime. Okay? So just like when I go through the universal cover of the circle, transporting is the successor function. Transporting with this fibration is multiplication by A. Okay, so you can calculate that by beta reduction from that definition. And the other fact that I'll need is that transporting at codes on the inverse of mer A naught, where A naught is the base point of A, on A prime equals A prime. And the reason for that is that transporting at mer A, the action of codes on mer A naught is multiplication by A naught. But in the definition of H structure, we stipulated that multiplication by A naught is the identity. Okay? So mer A naught goes to multiplication by A naught, that is, goes to the identity, and the inverse of the identity is the identity, so this is the identity. Okay? So you can just calculate that. It's like 3 or 4 lines of proof. Okay, so now what we need to do is we need to define encode, which goes from, for all x in the suspension of A, so let me write P of x. Here, let me just define. P of x equals the one truncation of the loop space of the paths, one truncation of the paths in the suspension of A from north to x. And codes is already there. So I want a function from P of x to codes of x, right? P is just abbreviating the stuff that I wrote up there, right? Right? Okay? Okay. Which is just defined by encode sub x of alpha equals transport at codes of alpha, and then I need some base case, where the base case is in codes of north, and the appropriate element to pick is A naught. Okay? So just like when I do the proof for the circle, I start with 0, and I lift the path up into the cover, and then look at the action on 0. Here I lift up into the cover and look at the action on A naught. Okay? So that's one of my maps. And then my other map, let's call it decode. Is defined by, okay, so let's define decode prime, which goes from, let's just do this one. Decode prime is going to go from A to P of north, which is, of course, the one truncation of paths on suspension from north to north. Okay? So how do we actually get, given an element of A, how do we get that path, right? This is like, I think we've drawn this diagram before, but I've got north and south. I've got A sitting here. Now I've got decode prime of an element of A, okay? So that goes like that, that goes like that. So what I've got here is an element of A, right? And I want a path in the suspension from north to north. And I want it to be sort of the thing that encapsulates A in that path. But what I've also got is the base point A naught over here, right? So if I want to make this path, what I do is I go down along the meridian at A, and then back along the one with the canonical base point at A naught. Okay? So decode prime of A will be the meridian at A naught backwards after the meridian at A. Okay?
And you don't need the truncation for that.
No. So like I define the path and then I inject it into the truncation. Yes, that's true. Okay. So now we've got our maps encode and decode prime. One of the composites is kind of like the easiest one of these that I've ever done, so I might as well do it. If we want to check that encode of decode prime of A colon A equals A, right? So we've got our two maps back and forth. We've got encode and decode. We want to check that the composites are the identity. One of those is showing that for any A in A, this thing gives you back the same path from north to north, okay? And that's actually just like immediately obvious given what we've already said, because encode is by definition transport at codes with decode prime of A starting off at A naught. But we know what decode prime is, so this is the same as transport at codes of, let's see, decode prime is in the truncation mer A naught backwards compose mer A starting off at A naught, okay? And I told you before, so transport at codes, codes is a fibration. Remember codes is, no, sorry. This is just transport at codes, right? So, no, sorry. Codes kills the truncations. Anyway, like just codes kills the like outer brackets around there, just because of codes is. Why does codes kill this?
So those are going to wind up canceling, and then you'll transport the identity.
Yeah, exactly. So like once I expand it, just take my word for it that somewhere those, I got a little lost in the calculation, but somewhere those truncation brackets get killed. And like otherwise it wouldn't even type check, so like they must. OK, so transport at codes. Now we apply functoriality, so what we get is transport at codes of mer A naught inverse on transport at codes of A with A naught, okay? And then the two reduction rules that I gave for transport at codes tell you that this will turn out to be A, because first you get that this one equals A times A naught, which is by the property of the H structure A. And then we said that transport at codes on mer A naught backwards on something is the identity, because mer A naught gets sent to the identity, the inverse of the identity is the identity, and therefore you get that that equals A. Okay? So you check that direction of the composition. And then the only thing that's left to do, really, is, I won't have time to do it in full detail, but I'll give you a hint for how it goes, is to show that decode prime, which is our map from A to paths in the suspension of A from north to north, extends to a polymorphic decode that goes from, for all x in the suspension of A, p of x, sorry, decode goes from codes of x to p of x. Okay? So it suffices to show that you get a fiber-wise map backwards, because once you have the fiber-wise map backwards, we've already checked that this composite is the identity. And to check that the other composite is the identity, you're in a situation where you're taking an element of the suspension and then an element of a path vibration. So you just use J, contract it to the identity. It suffices to check it on the identity. And on the identity, it's easy because it's transporting with the identity on A naught, and then like it works out. Okay? So like suffices to show that you get a decode. And the only trick to defining decode, it's basically just a little calculation. It's like that much text. But since it's almost lunchtime, I won't go through it. I'll just mention the one interesting thing which comes up, which is that you need to know, in order to do decode, that the map we just defined, decode prime, is a homomorphism. So you need to know that decode prime of A multiplied by A prime equals decode of prime of A after decode prime of A prime. Okay? So this is our map that sends points in A to paths on the suspension, right? So this is one of our two maps, right? At the end of the day, really I'm proving that this is a group homomorphism, so we need to know that this preserves composition anyways. But in the middle of this proof, when I do the calculation, I in fact need to know this homomorphism property just to check decode. Okay? And this is a little bit weird, because what I've got here is, if you expand it out, let me just write out what it suffices to show. It suffices to show that so the meridian constructor for the higher inductive applied to A compose A circle dot A naught inverse circle dot A prime equals the meridian constructor applied to, or no, sorry. The meridian constructor on A compose, in the sense of paths, the meridian constructor on A naught prime, A naught backwards, compose the meridian constructor on A prime equals the meridian constructor on A times A prime. So if you expand it out and cancel a few things, then it suffices to show this, okay? Like, just because, like, basically it's that with this multiplied on the left-hand side of both of them, okay? So it suffices to show that. And the only weird thing about this is that from nothing, we need to know that the meridian constructor for a higher inductive preserves this H structure multiplication operation, okay? So that's a little bit of a weird property. And when I first saw this, I was like, uh-oh, like, can we even prove this? Like, what's going on here, right? Because, like, I don't have very much to do, like, very much that I can do with this meridian constructor. Like, it's not obvious how to eliminate or anything like that, okay? But it turns out to be true. And the way that you prove it is using connectedness. In particular, the fact that A is zero connected, and the wedge into the product elim that Peter Lumsdaine came up with in the proof of Freudenthal. So there's this wedge into the product elim that says that when you have a connected type, if you're trying to prove a binary property of it, it suffices to check it on the axes of the, so like if you have like, in this case you have A, which has, so you're trying to give like A cross, so you're trying to prove P of x, y, where x and y both have type A, where P is this statement and x is that. Here, let me rename. P of A and A prime, okay? Let P of A and A prime be this, okay? Peter came up with this awesome induction principle for proving things about pairs of connected types, okay? Which says that when you're doing it, it suffices to show P of A naught and A prime, P of A and A naught in a, let me just say this, coherent way. So Peter talked about this one in his talk on Freudenthal, and I'm using exactly the same lemma. Like, I'm really just like applying the lemma that was already in the library. But it suffices to do it separately. And the thing is, when you do it separately, if you plug in A naught there, and if you plug in A naught there, that cancels. And if you plug in A naught there, that cancels. If you plug in A naught there and A naught there, then here you squish it inside, here you squish it outside. Okay? So it turns out that you can prove that the meridian constructor for the higher inductive, in fact, does preserve the composition using this connectedness argument and the wedge into the product kind of elim to get the result to go through. So that was pretty cool because I was like, uh-oh, like this, I mean, so like if this is going to turn out to be a group homomorphism, this must be true. But at first I didn't know how to prove it. And then I was like, oh, we can do a connectedness thing. And magically it works. Okay? So that lemma is pretty cool. OK, so just to summarize, where we ended up, like this is basically 90% of the code. So the code is about like 250 lines. I wrote it down. Like 250 lines of code for the first thing we did, the KG1, and then another 350 lines of code for the KGN. And like I've been through almost all of it. Like everything that's left is kind of a routine calculation or screwing around with numbers and indexing and stuff like that. But like this is a pretty good sense for what the code looks like. And then we get a type where you pick an abelian group, you can stick it in pi n of any of a space. OK, thanks.